right. So we are on lecture 1-2, feedback control system block diagrams. All right. So we've got, this is the last lecture of chapter 1, which is just sort of an introduction. So getting some sort of preliminary ideas, I guess, introduced. So a useful tool for designing control systems is the block diagram, which we've seen before, right? We've seen the block diagram in system dynamics, the portion that we did earlier of this course. The plant and the controller are represented as blocks. So here, this is an example. This would be the plant. Remember, the plant is the system that we would like to control, right? That's the definition of the plant. So it's going to have some transfer function, g of s. And we're going to also have a controller. So this one is our controller. And it has transfer function c of s. So not every controller has to have a transfer function defined. If it's nonlinear, then there is no transfer function definition for it. If it's based on like fuzzy logic or machine learning, then it's not going to have a transfer function associated with it. But in this class, we're going to consider just controllers that have transfer function descriptions, which describes the vast majority of controllers. So we're good. Some like newfangled controllers that the hep cats are into, they don't have transfer functions, but that's okay. We'll get a long way with our transfer function representation. Hep cats, I don't know. Okay, so a typical block diagram is shown below, and we've used a transfer function to describe each of these two important blocks, the controller and the plant. Now let's go through around this loop. So this is the block diagram that we're going to focus on for feedback control in this class. There are alternative block diagrams that do equivalent things, but I think this is the most intuitive way to represent it. And so remember, the output of our controller is the input to our plant. And that's how we're going to control the plant, through its inputs, right? So this is our sometimes this is called the control effort. It's the input to the plant, but it's the control effort. And we'll often use the symbol U for that. I'm going to use capital letters in the block diagram because we're often thinking in terms of the Laplace domain and transfer functions in the block diagram. You can use lowercase letters in the time domain and all that, but it's preferable to think in terms of the Laplace domain in a block diagram. So the output of the plant is the output of our control system, or of our entire control system, or our closed loop control system that we'll discuss in a moment. So I'm going to suppress the of s just because it's a little cleaner. Y is the output. This is the variable we want to control. Assuming it's a single output system, we want to control that output. Maybe there are multiple outputs, we want to control multiple outputs. But we're going to focus on single input, single output plants. And if you do the Control 1 course in the fall, we'll talk about multiple input, multiple output plants. So this output gets fed back. So remember, we're using the concept of feedback, so we're going to use feedback here. We'll measure it, measure what that output is. Maybe it was the angle of the robot arm joint that we talked about last time, so maybe we want it to be 30 degrees of the output. Let's measure what it actually is, feed it back, and we're going to subtract it in the summing junction from the command value for the output. So the command, we usually use R for the command. So it's the command minus the output. So it's the difference between what we want and what we actually have, which is just often too damn large. Am I right? No. It's okay. It was a bad joke.
Bad dad joke.
It was probably a bad dad joke. I think that most of my jokes are dad jokes. I do have a son named Niles. He thinks he's a real boy. He's a dog.
Okay.
He's a goofball though. He thinks, yeah. This morning I had a hard time getting out of bed because his head was laying next to mine on the pillow, and I was like, "Aw, so cute." I was just cuddling. So yeah, that's my life. It's fun. Okay, so the difference here is the error E. So we want the output to be whatever we command, but if there's any difference, then that's going to be an error for us. We give that error back to the controller. The controller decides what control effort to apply to the input of the plant to try to make that error 0, to try to continue to drive that to 0. So a lot of what we're going to do from here on out is explore what the implications of different things going on in C have to do with the performance of the control system. Okay. So specifically, we want to make the output Y equal to the command R, and we have different performance criteria. I mean, obviously, there are questions of time, like how much time do I have to go from some non-zero error to a 0 error? Does the error really need to be 0? Can it just be small? There are other similar questions that we're going to explore in the coming sections. And in fact, the first one we'll consider is stability. So when I try to make the difference between the command and the output 0, and I try to make my error 0, do I instead make my error infinity? Well, that would be good to know as well. So that's like the first performance criteria. It's like stable's good. We should shoot for that. Just generally. Okay, so recall that a block diagram can be considered to express algebraic relationships. So that's all it does. It doesn't describe any sort of loading situations. It just describes algebraic relationships. Yes?
So with the error, so if you have like a skew, like you're trying to get to 60 miles per hour, but every time you put the command to get to 60, it goes to like 55. So you have like a constant error?
Yeah.
Is that what we're looking for?
That's called a steady state error. And we're going to be talking about that in chapter 4, I believe it is.
Because this is error, like it's kind of like bouncing.
Yeah, so that would be transient error. So we're going to look at performance from the perspective of the transient response, which is like how long does it take to decrease the error, and like does it overshoot, the error overshoot, and all that. And then we'll consider after that the steady state error. So like after it's done like changing and bouncing around, like if you have cruise control that's set at 60 and it just like hangs out at 55 and never gets to 60, that would be a steady state error. So we're going to look at both of those.
Okay, so this error is encompassing all three, or is this error specifically looking at the change between command and output?
So this error is looking at both transient and steady state error. So it encompasses both of them. So yeah, so your error here is, often we think of this as being like the instantaneous error, but if you look at the instantaneous error over time, it describes all of the error. So yeah, good question. So this block diagram, like all block diagrams, just express algebraic relationships, right? So in a lot of ways, we could have written 3 equations instead of drawing the block diagram, but the block diagram is a little bit more intuitive. It gives us a visual representation of how the system's connected, so that's why we like it. But we've got 3 algebraic relationships defined by this. One of them is defined by the summing junction, which says that the error is equal to the command minus the output. So that's the first equation. E equals R minus Y. So that's just a basic algebraic equation that's expressed by the summing junction here. The second one is when you go through the first block, the output of the first block is just the input of the first block multiplying the transfer function. Okay, in the Laplace domain, that's what the output is. And so that's what the second equation is that U equals C times E. Similarly, with the plant block, the output is equal to the plant multiplying the input control effort U. So that's just using the definition of a transfer function, essentially. The transfer function is the output over the input, so the output is just the transfer function times the input. So we've got 3 equations described here. And like for me, looking at these 3 equations and looking back at the block diagram, I feel a lot better looking at the block diagram. But when you actually need to do algebra, you got to write those equations down, right? So there's that. Okay, so here are the 3 equations that are defined in that figure. So let's do a quick example, which actually we're going to derive something of interest to ourselves as we go forward. So this is a learning example, not just like an example of a problem to work, but this is like a derivation kind of example. But given the block diagram above, solve for the closed loop transfer function y over r. So the closed loop transfer function, you had a homework problem on this in system dynamics, but I didn't talk about it in class. But the closed loop transfer function is defined as being the output over the command. Okay, so that we would like this output to follow the command as closely as possible. So if you want to know how the system responds to some command coming in, you look at the output over the command as a transfer function, and then you can use it to predict what will happen when you put in a given command. Now, this transfer function can be derived from the 3 algebraic relationships defined in the block diagram. So let's go ahead and use those 3 to find out what we're working with here. So I'm gonna suppress the of s here because it just gets a little messy. So y equals, from the equation that we have that's solved for y already, I'll call this equation 3, 2, 1. So from equation 3, we've got y equals gu, and from 2, we have that u equals ce, GCE. Now, let's take a breath here and let's think, okay, we're just plugging stuff into algebraic equations. We're looking for y over r. We think we're probably going to have to use all these equations to describe what that relationship is. Generally speaking, we want an equation that has just y in it and r in it and transfer functions, right? So C and G are okay to have in there, but we don't want to have E in there, and we don't want to have U in there, okay? So we got rid of U, and we picked up an E, so we got to get rid of E. Let's use equation 1 for that. So we have G, C, and then instead of E, it's R minus Y. And now we've actually eliminated U and E, and we have Y on both sides. So if we solve for Y, we're looking for the ratio Y over R, it stands to reason that a good approach would be to solve for Y and then try dividing both sides by R, and hopefully the R will fall out of the other side. And if it's a linear system, this will happen. So It's good. Fortunately, we're working with a linear block diagram description. So we can solve for y by bringing this y term over to the left-hand side. So we have y plus g c y equals g c r. We can then factor out y and divide by what's left when you factor out y. So y equals gc, when we move the r out front, divided by 1 plus gc. All of that times r. Now, my question is, why do people always say Gucci? I don't know. It's confusing to me.
That's so random.
GC. Why do people say it?
Because Gucci is expensive.
Yeah. Okay. Gucci.
Nice and expensive.
So it's like, so that's like, it means like good. It's like
It sounds Gucci.
Gucci. That's Gucci.
Sounds rich and nice.
Okay. That's Gucci. All right. I'm probably not going to use it. Maybe I will. We'll see. To be determined. So we've solved for y, and now if everything works well, if we divide both sides by r, the r will fall out from the other side, and it does. It just cancels right out. So we have y. Oh, I didn't put my implies. Dr. Amendi would be disappointed in me. Isn't she a stickler for that? I've heard she is. I don't know.
Notation?
Yeah, like you should put like this implies, therefore, and not be sloppy with your notation. I am usually pretty good. I apparently have some y over r. I have some mathematician in my super ego or something. Super ego. I'm a Freudian. I like Freud a lot. Nobody in Olympia likes Freud, though. They're all Jungians here.
Sigmund or someone else?
What? Sigmund? Sigmund, yeah. Sigmund's my guy. I like him. Actually, I like Jacques Lacan. He's a Freudian. It's a long story. It's Gucci. So there's our closed loop transfer function. Y over r. So this transfer function will tell us, okay, if you say, so originally, remember, before we had this closed loop going on, we just had a plant and we had control effort going in and output coming out. And so if you can imagine, we're say we have a dial on a motor, okay, like for the voltage input to the motor, and we want some output thing to be going a certain speed. So before we had all this feedback, we were sitting there with a dial, and we were like turning it up, and then we were like, oh, it's getting there. We slowed it down, and then we turned it up, and we tried to like coax it right in there to the right speed, right? Okay, that's how we would be doing it. But we didn't have feedback, so like really we were doing it in the dark. We didn't even know what it was really doing. We were like, I think this will get it to the right speed. Okay, then we did feedback, and when we have feedback, we have this controller in there. Now we can just say, all right, go to 1,000 RPM or whatever. And then the controller hopefully will decide what to put in to the system to make it go, what voltage to put in. So it'll do the knob thing. We just say 1,000 RPM for a command, and then the actual output will hopefully go to 1,000 RPM eventually. So we've upgraded our control because we've got this automatic feedback control system put in, which is pretty cool. But we still do. I mean, we have to put in like, what do we want it to be? We got to put that in, And then the question that remains is, okay, what actually happens? Like we say we want the command, we want the output to be 1,000 RPM. What is it actually doing? And that's what we're going to be looking at. So like, and how do you choose the controller to make that happen as quickly as possible? I mean, if you do like an instantaneous change from like 0 to 1,000 RPM on your like dial, or like you type it in, 1,000 RPM, go. Clearly, it's not going to be there instantaneously. It's going to take it a second to speed up, right? So you gotta think of there being this like, okay, there's going to be this response. Hopefully, it will eventually get to 1,000 RPM, but maybe it'll get to 900 RPM and get stuck. So that's the steady state error question. But in the transient section, like how does it get there? Like, is it okay for it to go faster than 1,000 RPM for a second, or do we need to keep it below? Is there some sort of safety concern there, or other concern? So we've got different performance criteria to consider, including the most obvious being stability. If when we're like, go to 1,000 RPM and it flies off to 10,000 RPM and breaks, that would be bad too. So that's our first performance criterion, that it's stable. All right. Any questions on this? So this result, this closed loop transfer function result, we'll use even in the next lecture. So, Gucci.